Okay, here we have some examples. In each case, determine the moment of the force about point O. Okay, so here we have a force. Let's call it F. 100 newtons. We need to find the moment about point O. In this case, pretty easy. The line of action of the force goes here like this. So we have already the distance from the line of action of the force to the point O. So directly the moment is going to be equal to F times T. So it's going to be equal to 100 newtons times 2 meters equals to 200 newtons meters. Easy. Next. Questions? Not a problem with this one. Next problem. Very similar. You know what? Let me go back to this one right here. 1 second. In this problem, I would like to point out the fact that this force going down like this, it tends to show us some kind of rotation of the point O in this direction, right? And it's easy to see that if the force is strong enough or the beam that is showing there is kind of weak, it will rotate like this about point O, right? There will be some kind of rotation in this direction. So this is a problem where you can see the effect of the moment very clearly. The moment is trying to produce a rotation about a point. In this case, it would be nice if we also include here in the answer, the answer is 200 newtons rotation in the counterclockwise direction. That may be something interesting to add here to give the idea that in what direction is the rotation of the force with respect to the point O. All right, so let's go to the next one. In this one, we need to find also the moment of the force 100 with respect to point O. Again, the distance is given to us, is 1 meter, is directly the distance from the point to the line of action because this is 90 degrees. So the moment is very easily 100 newtons times 1 meter. So it's equal to 100 newtons times meters. And the rotation of this force with respect to that point O is now in this direction. So I would put here one clockwise direction. Even though here the beam is not going to rotate because there is a support here that doesn't allow the beam to rotate like this, right? Even though that is not going to happen, there is still the notion of the force going in this direction producing a rotation in this direction like that. So it doesn't matter if the rotation is actually produced, the moment has this effect of rotation no matter what, depending on the location of the point and the location of the force. In this case, this force with respect to this point produces rotation in this direction. If I put a point here, a force here, the rotation will be in this direction. If I put this point here and this force here, the rotation will be in this direction. You have to apply your common sense about how to visualize in what direction the force is making or is producing the rotation of the point. Next. Now this one. We need to calculate the moment of this force with respect to point O. Let's say this is force F. So here we cannot calculate the force as the moment as force times D because we don't have D. Why we don't have D? If say this is the line of action of the force, D will be distance measured from point O perpendicular to the distance where this is 90 degrees. We don't have this distance D here. We don't have it. We could find it, right? And maybe it's not that difficult. We will find an angle here and there with based on the dimensions. We have this information here that can give us information about the angle, so we can find this angle based on this using the arctangent of 4/3 or something like that. But it would be much easier and quicker if we calculate this moment using components. If we get the components of the force F, this is F here, this is F here. If we get this force, let's get rid of the line of action. If we get the components of this force in the y direction and in the x direction like this, so we have, this is the component in the x and this is the component in the y direction. We can call this one fx and we can call this one fy. We can find the moment of the force F as the summation of the moments of the two components. So we could have here the moment equals to the moment produced by the force Fx multiplied by the distance, that in this case, if you look at the force X, the line of action of the force X goes through the point. So this distance is 0. Let's call it, I don't want to call it I'm gonna call it distance X for now, but I don't like. Plus the moment produced by the force Y, which is Fy, times the distance from the force, this line of action, to the point O here, that with distance we have it here is 3. So this is times 3 meters. So let's continue doing it here. So the moment is equal to Fx. We don't need to calculate Fx because we know that this distance is 0. So this moment, it really doesn't exist, no matter no matter what value has the force, the x component. Now the force y, we can get it from this triangle here. So it's equal to F times 4/5 times 3 meters. So this moment will be 0 plus F is 500 times 4/5, this is newtons, 30 meters. So this is equal to 400 times 3, 1200 newtons meters. Okay. Now is going down like this in this direction. The point is here, so the rotation will go in this direction. So the answer, I would like to put it here some kind of like counterclockwise direction. Okay, makes sense? Let's continue. Another example. Let's see this one. This is similar. Again, I'm gonna repeat. If I have the line of action of this force here, and then if I have this distance from the line of action at 90 degrees with respect to O, if I have this distance, I could very easily calculate the moment as force times d. But since I don't have this distance, I don't have this way to produce the results. So in this case, it will be more convenient to work with components. If we get the components of the force here, the vertical component F, let's call it Fy, and the horizontal component Fx, based on the 3, 4, 5 triangle here, we know that Fx is equal to 500 times 4/5, so it will be 400 newtons, and Fy will be 500 times 3/5, so will be 300 newtons. And now if we get the distances for Fx, the distance of this line of action to point O is this 1 meter right here. And from this force, the distance from the force to the point O is this distance here that we have at 2 meters. So we can say that the moment of the force Fx with respect to O will be equal to 400 newtons times 1 meter. That will be 400 newtons meter. And we have to point out the fact that this force going in this direction produces this rotation about the point O. So that is a counterclockwise moment. And now for the moment of Fy with respect to O will be 300 newtons times 300 newtons Fy multiplied by 2 meters, so will be 600 newtons meters. And what is the direction of this moment? This force is going up here with respect to this point, is going to make it rotate like in this direction. So that will be a clockwise direction. So those two moments have different direction. So clockwise and counterclockwise. So in order to do the summation of the moments with respect to point O, we have to set up some sort of sign convention. We can say, for example, that positive is counterclockwise. So then when we set up the summation, we say counterclockwise is positive, so plus 400 because that's counterclockwise. 600 is clockwise, so that's negative 600. So the answer is minus 200 Newton meter. Since the answer is negative, it means that it is the opposite to this convention here, so it's clockwise. So this is clockwise. So the answer will be moment of the force F with respect to point O is equal to 200 newtons meters clockwise. That will be the proper way to express the result of this problem. You have to express the magnitude and in what direction is this rotation be produced. All right. Next problem. Let's go for this one. This problem, we have to determine again the moment of the force with respect to point O. Let's make it a little larger here. We have a 600-pound force applying that point here. So maybe the system of components is also convenient because I see it kind of difficult, more difficult, not difficult, but a little more elaborated to find the distance from the point to the line of action. If we make the decomposition, maybe I should make this a little larger, of the force in the horizon. You know what? It will be better if we do the composition of the force in the direction of the bar and perpendicular to the bar. That's another way we can do the composition here. So we have this component and we have this component. So let's call this component F normal to the bar and this one F parallel to the bar. This makes things very easy because sorry, I put it, no, that's okay. No, not very easy, but I think it's a little easier because the distance from Fn to the point O is given right here, right? You see the line of action here, and this is the perpendicular here. And the distance from this other force to the point O right here is given right here, 0.5 feet. So what we have to do is just basically find this angle here in order to get the components. Let me draw this one a little better. So I have this force here, and then we just need this angle. Let's put it here in green. This angle here, alpha. We just need to find alpha, and the angle that we need to get the composition of the and the angle that we need to get to get the components of the force would be this. Sorry, this angle here in purple here. This will be the angle that we need. Let's call it, well, I don't have a, let's see for a beta. Beta will be 20 plus alpha, and alpha is 30 degrees. So from here to there. So beta is 20 plus 30, 50 degrees. Easy enough. So here we go. Moment of the force, let's do with the normal first. Normal with respect to O will be equal to force normal times 5 feet. Force normal will be equal to force times sine of 50 degrees times 5 foot. So this will be equal to, the force is 600 pounds times sine 50 times 5 foot. So this will be equal, here very quickly, 600 times sine 50 times 5, 2,298 pounds foot. Now, in what direction? The direction of the force normal will be, the force goes in this direction, the point is right here, so it will be counterclockwise. Counterclockwise. Now, moment of force parallel with respect to O will be force parallel times the distance is 0.5, is this force right here. The distance is 0.5 feet. So it's equal to force cosine 50 times 0.5 feet. So it will be 600 pounds cosine 50 times 0.5 feet. Very quickly here, 600 times cosine 50 times 0.5 foot, 192.8 pounds foot. And this one goes like this, produce rotation in this direction, so it's a rotation also counterclockwise. So both are counterclockwise, so we just can add them up. This plus this. So the total moment of the force F with respect to O will be 2298 plus 192.8. This actually was 8 pound-feet. So will be equal to 2298 2,190 pound-feet counterclockwise. Okay. Next problem here. We need to find the moment of this 600-pound force with respect to point O. Let's take a look a little closer. Okay. It looks easy. Let's see. We have the line of action of the force here. We just need to find this distance. That's all we need to find. So it's a matter of a little geometry here. Let's see. So we have this 45-degree angle right there. So basically all we need to do is to find this distance right here, and the distance d will be 4 feet plus this distance. Let's call it x right there. So that x will be, if we take this 3 feet and get the horizontal projection here, that distance will be 3 feet cosine 45 degrees. And if we subtract 1 foot to that distance, that will be x. So let's put it here. X will be equal to 3 feet cosine 45 minus 1 foot. Right? So x will be equal to 3 cosine 45 minus 1.1213. So d, which is the distance that we need to calculate our moment, will be 4 plus x, 4 plus 1,213. They will be equals to 5.1213. Then our moment with respect to will be 600 pounds times 5.1213 feet equals to 3,072.8 pounds feet. And since this is going in this direction, the force goes direction with respect to point O produces a rotation counterclockwise. So this will be counterclockwise. So the moment will be equal to 370 pound-foot counterclockwise. All right. Let's see one more. Again, we need to find the moment of the force with respect to O. It looks like the 3D, but it's actually in the plane, in the 2D plane XY, in the XY plane. So here, if we can find the distance between, this is the line of action of the force AB. If we can find the distance from here to here, this is 90 degrees and this is D. So the moment will be 500 newtons times D. So let's see if we can find D. Well, it looks easy because if we get this angle, then D will be 3 meters sine of that angle. Let's put here a label alpha. Alpha can be found as tangent minus 1 of this over this. So which is 4 over 3. So tangent minus 1 of 4 over 3, that will be 53.13 degrees. So now D is equal to this distance 3 meters sine alpha. So D will be equals to 3 meters sine of 53.13. So D equals to sine of this angle 0.8. So 3 meters times 0.8 equals 2.4 meters. So the moment will be very easily 500 newtons times 2.4 meters. 2.4 times 500, 1200 newtons meters. If we are looking from the top, this will be this goes in this direction, so the rotation will be like this. It looks like a clockwise, right? But in this case, yeah, let's leave it like that for now, because well, will be some kind of like a clockwise direction, but we don't work in the space here for these problems. It's actually, you go with the right hand rule, strictly speaking, this will be a moment that is going as a vector in the direction of the negative z. So you could state that somewhere like it's a vector going into the negative z direction. But this should be good enough for the purpose of our class here. All right. And then one last problem. Let's see this one last problem here. It says, determine the moment of each of the three forces about point B. Basically the same problem that we have been doing here, 3 in 1. So let's do the moments of force F1, F2, and F3. So we go one by one. Let's see, going for F1. F1. In this one, it will be very easy if we get the composition of this force in the x and y direction, this one and this one. Why I say so? Because this force doesn't produce any moment because the line of action goes through the point A, so there is no moment there. So it's just the F1y component, the one that produces moment, and the distance is 2 meters. So that moment is gonna be moment of F1 with respect to O will be just the moment of the component Fy, F1y times 2 meters. So it will be equal to F1y will be F 250 newtons multiplied by cosine 30 times 2 meters. So that moment will be equal to 250 times cosine 30 times 2, 433.01 Newton meters, and that will be a moment in this direction. That will be clockwise. So I will put here clockwise. Now, moment of F2. Let's see. Same thing here. If we get the composition of this into the X and Y direction, the F2X doesn't produce any moment because the force, the line of action of the force goes through the point A again, so doesn't produce moment. So only survives the moment of force 2y. So the moment of F2 with respect to O will be equal just to F2y times the distance, and the distance from this force F2y right here to the point O will be, all this distance is 5 meters. 5 meters. So the moment will be F2y, which is F2 300 times sine 30, sine 60, right, from this angle here, sine 60. I hope everybody is very good at that already. Multiplied by 5 meters. So this will be very quickly 300 times sine 60 times 5. 1299. 1299 newtons meters. And the rotation of this one is also going down like this, so it produces a rotation in this direction, so it's clockwise also. So we have here clockwise. Now the last force. So we can make this a little smaller so we can fit the last calculation. Let's put it here. F3. In this case, I will do the composition again. So we have the force here, Fx, and the force here, Fy, will be F3x and F3y. So F3x will be multiplied by 4 meters. Is the distance from the line of action of 3x to the point O, this distance here, 4 meters. So I have that moment, the moment of F3x with respect to O will be equal to F3x times 4 meters, and F3x is, given this 3, 4, 5 triangle, is 3 over 5, 500 newtons. That's the 3x multiplied by 4 meters. So this is equal to 300 times 4, 1200 newtons meters. And that force 3x, the force is in this direction. The rotation with respect to point O here will be like that, counterclockwise. So that will be counterclockwise. And now the moment of O, of the force 3y with respect to O, will be force 3y times the force 3y is this force right here. The distance will be this distance, so 5 meters. So times 5 meters. So it will be force 3y will be, given this 3, 4, 5 triangle here, this force 3y will be 500 times 4 over 5. 4 over 5 times 500 newtons times 5 meters equals to 2000 newtons meter, and this force goes in this direction. So with respect to this point, it's going to do rotation clockwise. So this one will be clockwise. So the moment produced by force 3 will be the summation of the two components. The moment of force 3 about point 0 will be equal to this plus this, but we have to be careful about the signs. So let's put a sign convention here. Let's do counterclockwise positive. Counterclockwise positive. So for the moment of F3, we say counterclockwise positive, so 1200 newtons meters positive and minus 2000 newtons meters because that one is clockwise. So then the moment of the force 3 is going to be minus 800. Since I got negative, it means that it's the opposite of this, so it is clockwise. So the moment of the force F3 with respect to 0 is equal to 800 newtons meters. 800 newton meters clockwise. And then we have the other two answers from here and from here. So we have here moment F1, let's move this down. Moment F1 with respect to O equals to 433 newtons meters clockwise. Moment of F2 with respect to O 1300 newton meters clockwise, and the other one we have it right there. Well, let's put it to be very organized, put it just down here. Moment 0 F3 equals to 800 newton meter clockwise. So all of them are clockwise. So let's put it in a nice shape here. The final answer. Okay. That would be it for now. I recommend you guys to take a look at problems example 4.1 in page 123 of your textbook and example 4.5. 4.1, 123, 4.5, page 133. I skipped the treatment of the cross product for a moment, which is very convenient for 3D applications. Since we are not doing the 3D application of moments in here, well, I better skip that because that makes a little bit complicated. For 2D is just enough for the treatment that we are doing here. So skip those. So that's why I'm skipping examples for 2, 3, and 4. Examples for 1 and 4, 5 will be good for you guys, and find examples in other sources and in other books. All right, see you next time.